Welcome to part 2 of the lecture on reinforcement learning. I want to start with discussing a few important distinctions within this area. So the first distinction is passive versus active learning. The second distinction, between on policy and off policy. And the third aspect is exploitation versus exploration strategies. And the fourth aspect is model-based versus model-free reinforcement learning methods. The two first distinctions are rather much related. So let's start with the first, which is the distinction between passive learning and active learning. So, of course, all agents in all these scenarios perform actions and get reward and so on. So it's not that passive means doing nothing. So actually, the original scenario that we talked about, reinforcement learning, still holds. With a cycle of actions, reward, etc., etc. The difference here is that a passive agent executes a fixed policy, which means that you can say this is an agent with no free will. One can consider it that this policy can have been given to the agent, and the agent is not allowed to change it. So the only thing that the agent can do is to act, but always according to a predefined fixed policy. What the agent can do, it can evaluate what's happened. It can look at what rewards it gets. It can look at the returns, etc. And it can also learn about the utilities of being in its various states. But it's a suspicious circumscribed existence. In active learning, the agent can update its policy as it learns, and of course there are different modes of that, and it can do that also while acting in the world. And of course, an active agent must consider what actions it takes, what their outcomes will be, how they affect the rewards, etc., etc. So the active learning scenario is where there is much more dynamic handling of the policy and its consequences. And of course, active learning is more typical, I would say, for the true reinforcement learning case than the passive learning. So what's very much related is this distinction between on policy versus off policy. Still, one can say that both these cases more relate to an active agent, because still, in both cases, we assume that the agent is interested in changing its policy. However, in the off-policy mode, you, at least for a period, stick to an invariant policy, but during that period, while still obeying that policy, the agent can learn in order to define a new policy that can be used in a later stage. So sometimes you call the actual policy that you follow for the behavior policy, and you call the one which you want to establish the estimation policy. The alternative is an on policy, situation, where you actually follow a policy, but incrementally and dynamically change that based on experience. So one can say that the planning and learning parts are interwoven, while in the off-policy case, the planning and learning parts are separated. The third distinction is between exploration and exploitation. So by that is meant that an agent, when it takes actions, can follow two different approaches. On one hand, that it could prioritize to follow paths already taken, where there already exists experience from those paths, from those episodes, especially by prioritizing those episodes, those paths that gave more return. The alternative is exploration, where you go into deep water, if I can use that analogy. So instead of just doing what you used to do, choosing what was good, not doing what was bad, there are of course a lot of avenues you never tested. So in the exploration, in an exploration-oriented policy, there is a strong ingredients of trying new paths. Of course, with the ambition and hope that those new paths should be more rewarding than the traditionally tried out ones. Of course, then there is an issue for the agent to decide on the trade-off between these two, because obviously it can make sense to do both at various points in time and under various circumstances. So kind of a little more static way of managing this balance is to actually be more explorative when you have a rather weak knowledge or rather incomplete view of the environment. But when you feel or you can experience that you have a more substantial knowledge about the situation, you could rather fall back on the tried out paths. But this is more like doing this in one period and doing the other in another period. A more dynamic method, which is, for example, this one called epsilon greedy, really do this judgment with a finer granularity. So actually, what one do is one define a little window. So if you have an action which satisfies, which has a probability very close to 1, then you keep to that. But if you cannot find actions with such high probabilities, then you turn to exploration. In general, of course, this distinction makes more sense with reference to the earlier distinctions for the active case rather than the passive case. I mean, of course, somebody can give you a predefined policy where you should explore, but as you have no free will, especially the trade-off discussion is irrelevant. And of course, exploration versus exploitation may make sense both in an off-policy situation and an on-policy situation, but one can assume that this way of dynamically balance between these two makes more sense in the online active case. Finally, we have the distinction between model-free and model-based reinforcement learning. So we still talk about the situation where our knowledge about the environment is not complete, which means that the complete picture in terms of transition function and reward functions are lacking. But actually there are then two approaches here. What's called model-based is the following, that we realize we have an incomplete model of the environment, but our approach will be to first to complete that model, and using certain schemes. When we think we have completed the model to the point we find acceptable, we regard it as complete and fall back on the, let's say, the dynamic programming approach, which we already realized works well for the complete knowledge case. So that's the model-based approach. The model-free approach is that we give up the goal to complete the knowledge. So actually we give up the quest for completing the transition relation and the reward relation. Rather, we work directly with estimates of the utilities. One example of that is Q-learning that we will talk a little more about, and where you set up a special measure, Q value, which is a particular kind of utility value where you don't explicitly, which you don't explicitly have to base on the transition and the reward functions. What we will do now is that we will look at the various approaches to solve reinforcement learning problem in the case of not complete information. And we will talk a little about one particular model-based approach, which is called adaptive dynamic programming. And then we will mostly talk about model-free approaches. We will talk about an approach to doing a direct estimate of the value function. We will look at Monte Carlo, something called Monte Carlo situation, and we will talk about temporal difference learning. And finally, we will exemplify that with a method called Q learning. So, as you can see on the pictures here, you can get a flavor for a very rough difference here. So, adaptive dynamic programming, as it is model-based, it falls back onto the build of a complete model and then applying dynamic programming. And I hope you remember now that dynamic programming does an exhaustive walkthrough of a breadth-first character. So obviously this fits well with the picture you see here. So it actually tests all routes up to a certain point. In contrast to that, a Monte Carlo situation is a method where you make samples. So you select samples of episodes, and this considers the rest, and you base your estimates just on those episodes. So one can say that a Monte Carlo simulation take few routes, but take them all to the end, to the terminal point. In contrast to that, the temporal difference methods are actually still follow a specific path, but do that in a more shallow fashion, not always following up the whole episode, rather looking at pairs of states and the differences between pairs of states. So the simplest method, and it's actually model-free because it's in the sense that it's not actually need the complete the transition function or relation, and doesn't need a complete reward function. So actually this is a very straightforward method where you look at a sample of epochs or episodes, and then you accumulate the averages along the way for each episode. So here they are in this method they introduced another measure called reward to go, and actually reward to go is just the sum of possibly the discounted rewards for each step in the episode. This method keeps a running average over all these rewards to go for every episode it looks at. So, and then it sets the value function to that average of all these. I mean, reward to go is not exactly the same as the return, as we already defined it, so it's a slightly different thing, but anyway, it's somehow accumulated reward, and it's for all episodes. And then you repeat, you take more samples, and depending on how many trials you take, when the trials go to infinity, theoretically the sample average should convert to the true utility for the state. The only problem is this is very time consuming, and the convergence is very, very slow, but otherwise it's very straightforward. The model-based approach we're going to discuss is called adaptive dynamic programming. Actually, this is an approach. This is very close to how I generally describe the model-based approach as such. So actually, what you do is to first to complete the partially known MDP model, which is to complete the full picture of the transition function and the reward function, and then after that you apply dynamic programming as in the simple full knowledge case. So therefore you have some strategy to learn this function, and mostly it's a straightforward approach there. So actually you collect examples of rewards for this kind of state action triples, and you collect examples also of the transition triples, and you take average of collected rewards, and you calculate the fractional time a certain action leads to a specific other states. So it's basically making a lot of observations of these kinds of triples, and then making some statistics based on that. So then you in a way define these two functions based on that material. Now we will turn to a model-free learning approach called Monte Carlo simulation. So Monte Carlo methods are computational algorithms that are based on repeated random samples to estimate some target property of a model. And actually Monte Carlo simulations simply apply Monte Carlo methods in the context of simulations. So then Monte Carlo reinforcement learning methods learn directly from samples of complete episodes of experience. So this is a limitation. This method is built on the analysis of one complete episode, starting with one state and ending in a terminal state. So Monte Carlo methods is model-free, no explicit model of the transitions or rewards are built up. So the method takes mean returns for states in all the sampled episodes, and the value expectation of a stat is set to the iterative mean of all the empirical returns for the episode. There are two variants here, slightly different. So in one method, you only consider the first time you come to a new state, because there may be episodes that passes state many times before it ends the terminal. But in the other approach, you just select or measure data, make observations for every state, doesn't matter how often you visit them. Here you can see an algorithm for first visit Monte Carlo. Every visit Monte Carlo version is very similar. It just modifies step 4 in the middle of the algorithm, so it considered states every time there you pass them, not only at the first occurrence. For the rest, the general idea with the algorithm is you generate episodes using the current policy P, and for each generated episodes, you go through the episode, and for each state, you potentially conditionally add a return item to the returns list. So in this returns list, you will get as many items that you have states, and then during all the iterations, you successively calculate the average, the iterative average for all the returns in the list. And then, of course, in every round, you set the value of function of the state to the that computed average on the return. When you've done that for an episode, you generate a new episode and you repeat it all over again until some convergence occurs. Actually, on the next slide, you can see how I calculate the incremental mean, but I don't have any more comments to that. So here you get a simple example that shows how the Monte Carlo simulation algorithm actually works. It's just two states, and you look at two episodes with certain structure for the rewards, and the formalism is explained in this slide. So and then you can see a pretty detailed calculation how things are done for the first visit Monte Carlo method. So there you can see that you calculate the return for the first state in the first episode, and then you calculate the return for A in the second episodes, and then you can see that the interesting item here is the average of those. So then the value function of R becomes the average, and they do the same for the second state, and a similar calculation will happen for the every visit case. So this is all very straightforward. The last thing we will do in this part is to look at another form of model-free learning, which is called the temporal difference learning, or TD. It's actually a class of model-free reinforcement learning, which learn by bootstrapping from the current estimate of the value function. So actually what this kind of algorithm does is that it's to take a sample from the environment, like the Monte Carlo situations, and then perform updates based on current estimates, like one doing the adaptive dynamic programming methods. So while Monte Carlo methods only adjust the estimate once the final outcome is known, which means that you consider the whole episode. So here, the temporal difference method adjusts predictions before the final outcome is known. So actually, it adjusts the estimated utility value of the current state based on its immediate reward and the estimated value of the next state. So actually, it's in principle update based on the relation to the next neighbor. So I assume the word temporal here is motivated by there's normally a temporal relation when you move from a state to another, and at the end you can see the updating equation, where you actually say that the value state, the new value state, is the old value state plus a certain parameter times the reward that you get when you take the step, plus lambda, which is this discount which you always normally have in this situation, times the estimate for the next state, minus the state you are in. So, and of course, by choosing different values of alpha and lambda, you can get slightly different functionality here. So this lecture will be continued soon in the part 3 video. Thank you.